In this video, we talk about the stack and about some memory addressing modes. Here's our first program. I copy the elf header from the last program, and I make a minor change. I was reading the System 5 ABI Supplement 386, Chapter 3, and it says that normally a text segment begins at big endian 8048000, not at 8048054, where my segment began in past videos. To comply with that, my text segment now includes the elf header explicitly. That is, in the program header, PV address changes from 54800408 to 00800408, little endian. Accordingly, P offset changes from 54, the beginning of the program, to 00, the beginning of the file. And P file size contains the number of bytes in the entire file, not just those bytes after the header. Now it's easier to compute the program length, as we no longer need to subtract the header length from the byte count at the end of the program. This program, 6a, prints hello world 3 times. The loop count is kept in register ESI, and we invoke a syscall write in the style of the last video. Program 6b is like 6a, but now let's suppose register ESI is no longer available to be the loop counter, nor EDI nor EBP. We could keep the loop count in memory at a fixed address and refer to that same address each time we read or write the value of the loop count. However, there's an address-free way to store things in memory. In 6b, we use register ECX for 2 purposes: the loop count and the syscall parameter buff of the write operation. The 2 purposes are fairly distinct. We don't need the loop count during the write operation, and we don't need the buffer address during the loop business. The idea is to store the loop count on the stack during the write operation. Instruction push R32 copies the contents of a 32-bit register onto the stack after extending the stack by 4 bytes to make room. Instruction pop R32 copies the last 4 bytes from the stack into a 32-bit register, then shrinks the stack by 4 bytes to reclaim the space. These handy little instructions are each just 1 byte long. Program 6c is like 6b, but instead of hello world, we print the stack each time through the loop. The stack is a last in, first out linear structure. In x86 chips, register ESP is the stack pointer. ESP contains the address of the data at the end of the stack, and the stack grows downward. That is, pushes and pops occur on the lesser end of memory. The stack occupies addresses at least ESP and less than ESP0, the value of ESP when our process starts. Here at the beginning of the program, we save the initial value of ESP in EBP, and we subtract 16, as we will be viewing 16 bytes of memory below ESP0. Here we print the 16-byte window, the first time through the loop, the number 3 is on the stack. The number 3 occupies 4 bytes and appears here in little endian byte order. The second time through the loop, the number 2 is on the stack. The third time through the loop, the number 1 is on the stack. And when the count reaches 0, the program exits. Program 6d is like 6c, but with another loop so that the 2 loops are nested. The output is 6 memory views. The outer loop count is pushed onto the stack. The inner loop count is pushed onto the stack, and the 16 bytes are printed. Just before the end of the inner loop, the inner count is popped from the stack. Just before the end of the outer loop, the outer count is popped from the stack. The outer count is 2, and the inner loop counts down. Then the outer loop counter is decremented, and the inner loop counts down again from 3. Program 6e is like 6d, but with the main code moved into a function body. Now we see how instructions call and ret store and retrieve information about the function caller. (6-1, 8-0, 0-4, 0-8). The address where execution continues after the function returns. Return addresses are kept on the stack. Now, I have a question for you. What happens when this program runs? There's a syscall exit. Register EBX contains the status for exit. EBX is initialized to 0 and incremented inside the body of this function f. Function f also messes with the stack. Here are a pop and a push. Function f is called a few times. When the program runs, is there an error like a segmentation fault or illegal instruction? Does execution reach the syscall exit? What is the value of the exit status? Go ahead and pause the video now. We run the program and the exit status is 3. Inside the function body, we pop a 4-byte value from the stack. That value is the return address of the function. After we add 5 and push the result onto the stack, the return instruction consumes the modified return address and skips 5 bytes ahead over the next function call. Function f is called not 6 times, but 3 times. EBX is incremented 3 times from 0. You might say that storing data on the stack can interfere with the function call mechanism. The x86 instruction ret expects to find on the end of the stack a return address left by instruction call. The state of the stack just before a function return and the state of the stack just after the function call should be the same. If we want to preserve the normal operation of the function call mechanism, while we also mess around with the stack using it to save data, we had better ensure that the same condition holds inside each function body. The state of the stack just before each return instruction and the state of the stack just after the function is called should be the same. Sometimes I use these annotations to keep track of the stack content and to stay out of trouble. Usually I don't include return addresses in the annotations, but I start the function body under the pretense that the stack is empty, annotate the data as it is pushed and popped, and make sure the stack is empty upon return. Often in practice, we need to store data somewhere, but we've run out of room in registers. In some cases, the stack is a good place to store things, and in some cases not. When it's not, we go back to storing data at explicit memory addresses. I cooked up a program to demonstrate some of the x86 addressing modes. This program moves characters H, E, L, M, O, and newline to an output buffer, then prints the buffer. What's special about this program is that characters are moved one by one, each character with its own addressing mode. We write H using a 32-bit displacement only. This mode with mod bits 00 and RM bits 101 allows us to provide an immediate address before byte 48 for H. At 7 bytes, this instruction is kinda long. We set EDI to OBUF plus 2 and write L at this address. We've seen this mode before with mod bits 00. There's a variation involving an 8-bit displacement with mod bits 01. The displacement, positive 1, goes after the mod RM byte 47 and before the immediate byte 4D for M. You may be wondering about the proper order of all the bytes in these instructions. The order is given in the Intel Manual, Volume 2, Section 2.1. The byte order is opcode, mod RM, SIB, displacement, then immediate. The next line has the same addressing mode, but here with a negative displacement. The displacement is signed, so -1 is written FF. The last two characters have modes with an SIB byte. An SIB byte is included when the RM bits are 100 and the mod bits are 00, 01, or 10. It's common to store data in structured records that are contiguous in memory, that is, in arrays. Then accessing fields within records involves some straightforward arithmetic. For example, the second byte of the fifth record in an array of 8-byte records beginning at EDI is denoted bracket 8 times EBX plus EDI plus 1, assuming EBX is 4. The x86 SIB modes offer a way to express all this arithmetic in a single instruction. Like the mod RM byte, the SIB byte has 3 fields. The fields are named S, I, and B for scale, index, and base. The scale field of the SIB byte is 2 bits long. Only a few scales are allowed, 1, 2, 4, or 8. The scale bits are 00 for scale 1, 01 for scale 2, 10 for scale 4, or 11 for scale 8. The index field of the SIB byte is 3 bits long. The index field indicates which register contains the index. In our examples, the index register is EBX, so the index bits are 011. The base field of the SIB byte is 3 bits long. The base field indicates which register contains the base. In our example, the base register is EDI, so the base bits are 111. In our program, EBX is 1, so bracket 2 times EBX plus EDI and bracket 2 times EBX plus EDI plus 1 are the 5th and 6th bytes of our output buffer. We have the RM bits set to 100. In this line, the mod bits are 00 for no displacement, and in this line, the mod bits are 01 for an 8-bit displacement, positive 1. In both lines, the scale bits are 01, indicating a scale of 2. In all these examples, we moved 1 byte at a time with instruction move RM8, IM8. But of course, there are instructions that deal with 4 bytes at a time, and there are variations on these addressing modes. See the Intel Manual Volume 2, Section 2.1. One more thing. As we've seen, these addressing modes involve a shorthand for small arithmetic expressions like 8 times EBX plus EDI plus 3. The value of such an expression has to be computed by the chip before the chip accesses memory at that address. If for some reason we want to use the value of such an expression without accessing memory at that address, the chip is nice enough to let us have it. The instruction is LEA, load effective address. In our program, we want to put OBUF into ECX. We formulate the memory location EDI-2, signified by mod bits 01 for a memory location with an 8-bit displacement, -2, and RM bits 111 for EDI. The middle 3 bits of the mod RM byte specify which register is the destination of this number being computed. That's due to the /R in the opcode column of LEA R32M. In this case, the register is ECX, so the reg bits are 001. The next 2 lines are much the same. LEA works with SIB modes as well, although I have no example. That's it for this video. We've collected many programming tools. In the next video, we're ready to tackle our long-standing problem of keeping byte counts and computing jump lengths automatically.